Hello everybody, my name is Shubham and I'm a research scientist at Ford Greenfield Labs. Today I will be presenting my work on VR3Dense. There are various methods for performing 3D object detection from LiDAR data, and they include both structured and unstructured point cloud methods. Similarly, various methods exist for monocular camera-based depth estimation problem. While they provide great results, features in one modality cannot take benefit of the features in other modality, and exploring that is the motivation for this work. In our approach, we first voxelize the point cloud and pass it through a 3D CNN to extract spatial point features. Simultaneously, we pass the left image through another 2D encoder-decoder convolutional neural networks. We then concatenate the spatial point features extracted from point clouds to the latent vector of dense depth reconstruction network, which is then decoded to output a dense depth map. At the same time, for final pose estimation, a set of fully connected layers are used to take in spatial features and regress object class and pose. Right camera image along with the encoded point cloud is also fed through the same pipeline to reconstruct a corresponding dense depth map. Both left and right dense depth maps are then converted to a left to right disparity map, and then a disparity consistency loss is employed to train the depth network in an unsupervised way. The disparity maps are further used to warp left image to right and right image to left. We then enforce consistency between warped and the camera image and train this using reprojection loss. Additionally, we use SSIM loss between the camera image and the reconstructed image during training. Since we do have access to sparse 3D point cloud during training, we project them onto image plane and use it to provide sparse supervision during training. We, however, found during our experiment that it is useful only during initial stages, so we decay the weight for this loss as training progresses. For the training of our 3D object detection network, we use supervision from ground truth poses. Detailed information about our approach is in the paper. Here we show the loss function for 3D object detection and monocular depth estimation. For depth estimation problem, we also introduce a new loss function called edge-preserving smooth loss, which enforces proportionality between depth and image gradients using learnable parameters. Here we show quantitative results for object detection and monocular depth estimation. This shows some qualitative samples on Kitty raw dataset for two different scenes. We also perform ablation study on depth estimation to understand effect of various loss functions. Please refer to our paper for more details. Thank you for your attention.